Hello, this is the section 11.1 part 2, and let's pick up where we dropped the previous part on vector operations in terms of components. So we now show how vector addition, subtraction, and scalar multiplication are performed using components. Well, suppose that we have two vectors, like in this example here, vector v with components v1, v2, and vector u with the components u1 and u2. Now, if we add those two, we can use the parallelogram rule here. We get the vector, the pink vector, which is the sum of u plus v. And the sum of u plus v, if you look at the components here, is actually sum of corresponding components. So I'm adding u1 plus uv, I'm sorry, u1 plus v1 and u2 plus v2, and this way I'll get the components for the sum of those two vectors. For scalar multiplication, again, if you just multiply each component by the scalar, this way you will get the components of the scalar multiplication. And the general vector operation works like as follow. Suppose that C is a scalar and U and V are the vectors with the given components. Then if we add the vectors, we add the corresponding components. So we add u1 and v1, and then u2 and v2, and if we subtract the vectors, we subtract from u1 v1 and then u2 v2, and then when we multiply by a scalar, we just multiply corresponding components of the original vector u. Now let's take a look at the example here. So we have the components of vector u and vector v, and our task here is to evaluate the magnitude of the sum of vectors u and v, and then simplify, perform the vector operation 2u minus 3v, and finally find two vectors half as long as u and parallel. First of all, if we would like to evaluate the magnitude of u plus v, then we need to find a sum. The vector, what is the vector u? Oops. What is the vector u plus v? So the vector u plus v is equal to, well, I'm just going to use the components and I'm going to add corresponding components. So I'm going to add negative 1 and 2. Okay, so I'll have maybe I will rewrite it first, negative 1, 2, and then plus 2 and 3, and now you can see how it works. So it's negative 1 plus 2, and then plus there you go. This is a comma, of course, comma, and then I'll add 2 plus 3. So these are the components of the vector, which are in this case 1 and 5. Okay, and in order to find the magnitude of the sum of two vectors, we just follow the rules for finding the magnitude. So I'm taking 1 squared plus 5 squared, and this is the square root of 26. Okay, so this was part A. Now for B, we need to simplify. So as you see, the length is the scalar here. Now if we would like to simplify 2u minus 3v, let me rewrite it again in terms of components. So I'll have 2, and the components for u are negative 1, 2. and then minus 3, and the components for V are 2, 3. Okay, so this is equal to I just first do the scalar multiplication, so I'll end up with negative 2 and 4, because that's what I get if I multiply by 2, negative 1 and 2, and then minus, and if I multiply by 3, I'll have 6 and 9 here. 6 and 9, and if I now subtract those, I'll have a negative 2 minus 6 and 4 minus 9. Therefore my components are negative 8 and negative 5. This was fairly easy, and as a result here I got the vector. And then for C, I need to find two vectors have as long as u and parallel to u. So basically what I have to do, I need to find 1/2 u, okay, which is 1/2, and u was negative 1, 2. These are the components. So this is just negative 1/2 and 1. And I have negative 1/2 u, which is negative 1/2, and the components, which is 1/2 and negative 1. So both vectors 1/2 u and negative 1/2 u have half the length of u and are parallel to u. Okay, they have different directions, but opposite directions, but they are half of the length of u. Okay, now let's talk about the unit vector. A unit vector is any vector with length 1. Two very useful unit vectors are the coordinate unit vectors. And first one is I, vector I, which is, you know, the vector with the components 1, 0, and j with the components 0, 1. And as you see, for both, the magnitude of I is equal to the square root of 1 square plus 0 square, which is the square root of 1, which is 1. So as you see, both have length 1. These are very useful vectors because sometimes we express all vectors in the form of I and j. Let's take a look. For instance, here we have vector, the pink vector here, and with the components 3 and 4. So basically we can express this vector here as a sum 3i plus 4j. In general, you know, the notation with the brackets here or parentheses here, v1, v2, is equivalent with the notation v1i plus v2j, where v1 and v2 are scalars and I and j are vectors. So sometimes you will see, you know, the vector v given by 3i plus 4j, and this means that basically the components are 3, 4, right? So that's just the notation. Okay, and now given a non-zero vector v, we sometimes need to construct a new vector parallel to v of a specific length. So dividing vector v by its length give us the unit vector, and we call it u. And because u is a positive scalar multiple of v, it follows that u has the same direction as v. Furthermore, u is a unit vector because as you see, if we take the if we take the magnitude of u, this way we will have v over v, which is 1. And also the same if we go with negative u. This is also a unit vector. Therefore, the unit vectors plus or minus v over length of v are unit vector parallels to v that point in opposite direction. So, so this is the short explanation. How do we figure out the non-zero unit vector? So again, this is a summary. The definition: a unit vector is any vector with length 1 given a non-zero vector v plus or minus v over the magnitude of v are unit vectors parallel to v. For scalar c greater than 0, vectors c v over absolute value of v plus minus are vectors of length c and parallel to v. Let's take a look at the example. This way we get better understanding of what we are doing here. So for this example here, we have points given P and Q, and we need to find the vector PQ and 2 unit vectors parallel to PQ. So let's start with at the beginning. So vector PQ is just, we use the components. So it is going to be 6 minus 1 and then 10 minus negative 2. That's how we find the components, and this is just 5 and 12. Or in other words, we can use different notation. It's 5i plus 12j. So this I and j signify the unit vectors or standard unit vectors in the direction of x and y axis. Now, so we found the PQ vector, and now we need to find 2 unit vectors parallel to PQ. So we know from the previous definition, we know how to do this. We just need to find PQ divided by an absolute, that's not it, that's the magnitude, PQ. Okay, so basically what we need to find out right now is the magnitude of the vector PQ. So the magnitude of the vector PQ, we use the components. This is 5 and 12, so we have 5 squared plus 12 squared, which is 25 plus 144, and this is equal to the square root of 169, which is 13. So unit vector parallel to vector PQ will be vector 5, 12 over 13. Right? Which is, in other words, in terms of components, this is 5 13ths and 12 13ths, or using different notation, it's 5 13ths I and then plus 12 13ths j. So this is one unit vector parallel to PQ. In order to get another, we just take this one with minus, right? Because we remember we can put plus or minus. So another vector that is parallel to PQ and it's a unit vector would be a vector negative 5 13th and negative 12 13th. So that's another vector. And then let's take a look at part B. We need to find 2 vectors of length 2 parallel to PQ. Well, so this is the second part of the previous definition. And so what we need to do, we just need to multiply the unit vector by plus or minus 2. So we can multiply the unit vector by 2. Let's use this notation here, 5i plus 12j, and this will be, oops, I forgot, that's the unit vector, right? So this is 10 over 13i, and then plus 24 24 over 13j. And if we do this for negative 2, we multiply the unit vector by negative 2. This is the result. This is j. So we will get negative 10 13th I and the minus 24 13th j. So you can go ahead and check and verify whether this vector has length 1. That's the unit vector, so you can just do this as an exercise. Now, as a summary, the properties of vector operations are as follow. If the vector addition is commutative, which means that we can add u plus v, and that's the same as v plus u. Also, there is associative property of addition for the vector. Additive identity is a zero vector. This is not a scalar here, it's a vector. And then additive inverse and distributive property. First we distribute the scalar over the vector, and then we distribute this vector over the scalar. Then multiplication by zero scalar, multiplication by zero vector, multiplicative identity, and associative property of scalar multiplication. So these are fairly clear properties of vector operations. Now let's take a look at the example, okay, at the applications of vectors. So let's consider the example here. Assume the water in a river moves southwest 45 degrees west of south at 4 miles per hour. If a motorboat is traveling due east at 15 miles per hour relative to shore, determine the speed of the boat and its heading relative to the moving water. So please, we have nice picture here. So here we see this is velocity relative to the shore. This is the velocity of the water, W, and then velocity relative to the river. To solve this problem, what we would like to do, we would like to set this within the coordinate system. If we go ahead and do this, well, now everything is clear. The pink vector is because the boat is moving east at 15 miles per hour, then VG is just a vector, you know, the vector with in the direction of the x-axis with the length 15. So the components would be 15, 0 here. To obtain the components for vector W, first of all, we know that the water moves at the speed, so we know the length of this vector. The water moves at the speed of 4 miles per hour, so we know that the length is 4, and then we can obtain the components. V X and Vy are the components of V, so W. So the components are wx and wy, and we would like to find out what are those. So you know, if we place this within the coordinate system, we see that we have a triangle here, and then Vy and Vx are equal to each other, and they are just equal to the W, the magnitude of the W cosine 45. Cosine 45 is cosine 45 is square root of 2 over 2, right? So basically the given orientation but for the southwest give us that we have the Vy is equal, because, well, the 4 times well, that's how it is calculated. Let's say Wx is equal to 4 times square root of 2 over 2, which is 2 square root of 2, and then you know, we have this because, you know, this is the right angle, so the other component Vy will be negative, right? That's the direction of the vector, so this is directed down, and yeah, so that's how we got it. So because here we know that the Vg is equal Vw and plus W, then let's do the calculation here. So this is equal to 15, so we are looking for Vw, and this will be I'm sorry, Vg to the with respect to the shore, and then minus W. So basically we know that this is 15 and 0, and minus, well, here we have minus square root of 2, 2 times square root of 2, and minus 2 square root of 2. So basically now if we simplify this, we will have 15 and then plus 2 square root of 2, and then 2 square root of 2. So this is the orientation, so that's the vector, and we need to find the magnitude of it. So the magnitude of Vw is equal, well, to the, we just square the components, so it's 15 plus 2 square root of 2 squared, and then plus 2 square root of 2 squared, okay, which is, well, approximately, this is 18. Therefore the speed of the boat relative to the water is approximately 18 miles per hour. The heading of a boat is given by an angle theta between Vw and the positive x-axis, right? Vw and the positive x-axis. The components of Vw, the x component of Vw is 15 plus 2 times square root of 2, and the y component is 2 square root of 2. Therefore we need to find an angle theta. Therefore the theta will be equal tangent inverse of well, the y components over the length, so over I'm sorry, over the x component, so it's 2 square root of 2, and then 15 plus 2 square root of 2, which is approximately 9 degrees. So the heading of a boat is approximately 9 degrees north of east, and its speed relative to the water is approximately 18 miles per hour. So that would be the solution here. And another very simple application here. Let's take a look. First of all, now suppose a child pulls on the handle of a wagon at the angle theta with the horizontal. The vector F represents the force extended on a wagon. It has a magnitude, well, the F, and direction given by theta. Okay, so basically, if we look at the picture here, we can find out components of the force by taking, well, this is my theta, so the x component of vector F is just the magnitude of F times cosine theta, and then Fy component is magnitude of F times sine theta. This is directly from the definition of the trigonometric functions. Now, for example, if we would like to look at the example, then we have that child pulls a wagon with a force 20 pounds at an angle theta equals 30 degrees to the horizontal, and we need to find the force vector. So basically we just follow this formula. Okay, we know that the magnitude of F is 20, and then we just go ahead and multiply this by cosine 30 degree, and here we have 20 and then sine 30 degree. Therefore, the vector F has the following components. It's the magnitude of F. I'm just going to rewrite the formula, and then magnitude of F sine theta, and this is 20 cosine 30 degree, and then 20 sine 30 degree, which gives us 10, because the cosine 30 degree is square root of 3 over 2, so it's 10 square root of 3, and here the sine of 30 degree is 1/2, so it's 10. And this concludes section 11.1.